Hello, my awesome chemists. Today we get to start chapter 10, which talks about the mole. So a mole is just a number. It's a word that describes a number. In the English language and a lot of other languages, there are many words that just mean a certain number. So for example, dozen means 12. So I can have a dozen eggs, I can have a dozen cars, I can have a dozen students. Dozen just means the number 12. Same thing with score. Score means 20. Or pair, it means 2. Or gross, it means 144. So just like these words just mean a number, a mole also is a number, but it's just a really, really big number. That number is 6.022 times 10 to the 23rd. It's a really, really big number. Here it is with all the zeros. Can you imagine that? So it just means that number. So I can have a mole of anything. I could have a mole of water particles. I can have a mole of students. I can have a mole of eggs. It's just that we usually describe or use it to describe very, very small things because usually we don't have that many of anything that's big. So a mole is this many representative particles. So if I have a mole of water, that means it's 6.022 times 10 to the 23rd particles of water. This number is called Avogadro's number. Amedeo Avogadro did not actually come up with that number, but he did do a lot of work with moles, and so they wanted to honor him, and so they called this number after him. A mole is an SI unit of measurement for amount. So like the SI unit for mass is grams, the SI unit for amount is moles. And we said that a mole of anything is 6.022 times 10 to the 23rd particles. Now, what are particles? Well, particles could be called different things depending on what type of substance it is. So if I have an element like carbon, then I'd say a mole of carbon is this many atoms of carbon. So it's an atom for elements. If I have something that's covalently bonded like water, then the smallest particle of it would be a molecule. So if I have a mole of water, that means I have this many molecules of water. And for an ionic substance like NaCl, we call the smallest representative unit a formula unit. And so if I have a mole of NaCl, then that means I have this many formula units of NaCl. So again, a mole is this many particles, and a particle can be, an atom, if it's an element, a molecule, if it's covalent, and a formula unit, if it is ionic. In terms of abbreviations, if I want to abbreviate the mole, I can write MOL, that's the accepted abbreviation. You don't have to put that E at the end. Atom doesn't really have an abbreviation because it's only 4 letters. Molecule, the accepted abbreviation is MOLEC, because if you stop anywhere before the C, then it looks like moles. Formula unit doesn't really have an accepted abbreviation, but for the purposes of this class, we're going to abbreviate it as FUN. F for formula, and then UN for unit. You have to put the N there, otherwise I'll take it personally. So FUN is formula units just for this class. So you know how when we balance equations, we put coefficients in the beginning there of your substances? Well, those numbers, those coefficients, can represent particles, so they can represent atoms, or molecules, or formula units. So for example, here I can say 2 atoms of aluminum react with 3 molecules of chlorine to form 2 formula units of aluminum chloride. Since this is just an element, this is an element but it's diatomic, and it so exists in molecules, and this is ionic. But those coefficients can represent particles, but they can also represent moles. So I can say I have 2 moles of aluminum reacting with 3 moles of chlorine to form 2 moles of aluminum chloride. So let's answer these questions here. It says how many moles of aluminum react based on the equation that's balanced here. So that would be 2 moles of aluminum. And then how many moles of chlorine molecules react? And so you'd say 3 moles of chlorine. And how many moles of aluminum chloride are produced? And so that would be 2 moles of aluminum chloride. So those numbers, again, represent either particles or they can represent moles as well. It's the ratio of the moles or the ratio of the particles. How many moles of manganese are in 3MnO2? So if we see this, well, this means that I have 3 moles of MnO2. So let me actually write MnO2 here. Let's say I have 1 dozen MnO2. How many dozen manganeses are there? So if I had a dozen of these, like, 1 manganese with 2 oxygen, I had a dozen of those. Then I'd have 1 dozen manganese. How many dozen oxygens do I have if I had 1 dozen of these? Well, I'd have 2, right? Each MnO2 has 2 oxygens. So a dozen of MnO2 would have 2 dozen oxygens. Well, now replace dozen with mole. So what if I had 1 mole of MnO2? How many moles of Mn do I have? Well, I'd have 1. How many moles of oxygen would I have? Well, I'd have 2. So now let's change it to 3 moles of MnO2, which is what we have right here. How many moles of manganese would we have? We'd have 3. How many moles of oxygen would we have? We'd have 6, right? So I'm going to change that to 3 there. So if I had 3 MnO2, that would tell me, like 3 moles of MnO2, that would tell me that I have 3 moles of manganese and 6 moles of oxygen. Now, a mole is a really, really big number. Avogadro's number is huge. We can't really comprehend how big that is. So here are some analogies to just kind of give you a perspective of how big this number really is. 1 mole of rice grains, so if I only had 1 mole, 6.022 times 10 to the 23rd rice grains, that would cover all the land area of planet Earth to a depth of 75 meters. 75 meters is like 75 yards almost. That's a lot of rice. And imagine rice is really tiny, like each rice grain is really tiny, but a mole is really big. 1 mole of rice grains is more than the number of grains of all kinds of grains grown since the beginning of time. We have not grown a mole of grains yet on Earth. That's incredible. 1 mole of hockey pucks. So imagine a hockey puck, how much, it weighs. 1 mole of hockey pucks would equal the mass of the moon. That's crazy. 1 mole of marshmallows would cover the entire Earth to a depth of 12 miles. I can't even see a mile ahead of me. So imagine Earth would be covered to a depth of 12 miles if we only had 1 mole of marshmallows. It's a huge number. Now this one's really outdated. This is probably like from 10 years ago or so. But back then, computers could count at a rate of 80 million counts per second. So a computer with this rate could go 1, 2, 3, 4, 5 to 80 million in just 1 second. So it's really, really fast, right? At that rate, it would take that computer 250 million years to count to 1 mole. Isn't that crazy? That's a big number. 1 mole of pennies would give every man, woman, and child in the world this much. How much is that? That's crazy. That's what, $1 trillion? Personal spending at the rate of $1 million per day would use up a person's wealth in 400 years. So you spend $1 million and you don't even have a mole, you only have this much. That's crazy. Life would not be comfortable though, because the surface of planet Earth would be buried in copper coins to a depth of 420 meters. So a mole is really, really, really big. But we need a huge number like that because particles are really, 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 really tiny. It's a big number. So let's take a look at worksheet 1. For all these, for the whole chapter, we are going to each day look at a worksheet or two. We'll do a few of them together, and then the rest of it would be homework for you to practice. So let's look at, I believe this is number 1 on worksheet 1. And it says, how many molecules of water are in 2.3 moles of water? So just a reminder, we said 1 mole is equal to 6.022 times 10 to the 23rd particles. And these particles can be atoms, molecules, or formula units, depending on if it's an element, a covalent substance, or an ionic substance, right? So we are going to be using conversion factors a lot in this chapter. And so since I know that 1 mole is equivalent to 6.022 times 10 to the 23rd particles, and the conversion factor is a fraction where the top and the bottom are equivalent, I can use this conversion factor. 1 mole is equivalent to 6.022 times 10 to the 23rd particles. Or I can say 6.022 times 10 to the 23rd particles are equivalent to 1 mole. The top and the bottom are equivalent, so they're kind of equal to 1 basically because you're dividing them by something by itself because they're equivalent to each other, so it's equal to 1. So we can use conversion factors to go from one unit or one substance to another. So let's go back to this one. It says how many molecules of water are in 2.3 moles of water. So we always write down what we have first, and we want to write the number, we want to write the unit, we also want to write the substance because later on we're going to go from one substance to another, and this is going to be really important that we write down the substance. I know it's a lot, but get in the habit of writing all that. So then we start my conversion factor, and what you want to do is you don't want moles of water anymore, you want molecules, right? So you want to get rid of these units. So since they're at the top, what you do is you put the same units on the bottom here so they cancel when you multiply it through. So I'm going to put moles of water here on the bottom so they cancel. On top, you put the units that you are looking for. So we are looking for molecules of water. So I'm going to write molecules of water here. Molecules are like a type of particle, right? So can I go from moles of a substance to its particles? Yes, I can, using this conversion factor, right? 1 mole is equivalent to 6.022 times 10 to the 23rd particles. In this case, the particles are called molecules because it's covalent. So next to the molecules, I put the 6.022 times 10 to the 23rd. And next to the moles, I put 1 because 1 mole of a substance is equivalent to 6.022 times 10 to the 23rd particles of that substance. So when I multiply this through, in terms of units, my moles of water and my moles of water here cancel because one's at the top, one's at the bottom, and I end up with my units as molecules of water. And then I punch this into my calculator. Anything on top I multiply, anything on the bottom I divide. So this is 2.3 times 6.022 times 10 to the 23rd divided by 1. So remember that in your calculator, when you punch it, hopefully you have your calculator with you. You punch this in with me. So go ahead and do 2.3, and then times 6.022. And then remember you do second comma, which gives you E, and then 23. You can divide by 1 if you want, or you don't have to. Anything divided by 1 is itself. So when you do that, you should get 1.4 times 10 to the 24th molecules of water. If you're solving for particles, particles are really tiny, so you're going to get a really big number. If you're solving for moles, you're going to get a reasonable number. So just remember that. we need 2 sig figs because this number is 2 sig figs and this number is 4 sig figs. Okay, let's try this one here. It says, how many formula units are in 8.6 moles of NaCl? So we're going to write down what we have, 8.6 moles of NaCl. And do a conversion factor. On the bottom, we're going to put moles of NaCl so it cancels. And on top, we're going to put the units that we want, which are formula units of NaCl. Can I go from moles of NaCl to its particles? Remember, formula units are a type of particles of the same substance. Yes, I can. Using this again. 1 mole is equivalent to 6.022 times 10 to the 23rd particles. So next to the mole, I put a 1. Next to the particles, I put 6.022 times 10 to the 23rd, which is Avogadro's number. Moles cancel. I multiply 8.6 times 6.022 times 10 to the 23rd, which gives us 5.2 times 10 to the 24th formula units of NaCl. Let's try the next one. We're going to go to number 5 next. So we're going to skip 3 and 4. You guys do that on your own. How many moles of tungsten are in 8.27 times 10 to the 21st atoms of tungsten? So I'm going to write down what I have, 8.27 times 10 to the 21st atoms of tungsten. Start a conversion factor on the bottom. I want to put the same units that I have so they cancel, atoms of tungsten. On top, I'm looking for moles of tungsten. Can I go from atoms of tungsten, which are particles of tungsten, to moles of tungsten? Yes, I can. 1 mole is equivalent to 6.022 times 10 to the 23rd. So like this one here, 1 mole is equivalent to 6.022 times 10 to the 23rd particles. So next to the mole, I put a 1. Next to the particles, I put 6.022 times 10 to the 23rd. Atoms of tungsten cancel. My units are going to be moles of tungsten. And on my calculator, I put 8.27 second comma 21 divided by 6.022 times 10 to the 23rd, or second comma 23. So remember, anything on top you multiply, anything on the bottom you divide. So go ahead and punch it into your calculator, see what you get. Make sure you're getting the same answers that I am. I got 4.7, oh sorry, no, 5. Oh, sorry, it's not right. I got 0.0137. 0.0137 moles of tungsten. Sorry, I was looking at the wrong one. So 3 sig figs here, 4 sig figs here, so my answer is 3 sig figs. Remember, leading zeros are not significant. So notice that sometimes I put the 6.022 times 10 to the 23rd on top, sometimes I put it at the bottom. Why? It depends on what units I'm given and what units I'm trying to find. But the 1 goes always with the mole, and Avogadro's number always goes with the particles. And notice that particles here were called molecules because it's covalent. They were called formula units here because it's ionic. And they were called atoms here because this is just an element, monoatomic element. Let's do a few more. Let's go to number 9. Number 9 says, how many moles of sodium are in 40.5 moles of sodium phosphate? So first I need to figure out what sodium phosphate is. This is ionic. Sodium is Na+, phosphate is PO4 3-. So sodium phosphate is Na3PO4. So we are given 40.5 moles of sodium phosphate, Na3PO4. Start your conversion factor on the bottom. You put moles of Na3PO4. On top, you put what you're looking for, which is moles of sodium. So it looks like we're comparing moles to moles. You can compare moles to moles or particles to particles of different substances. So when we use Avogadro's number, when we say 1 mole is this many particles, those have to be the same substance. Like sodium versus sodium, or sodium phosphate and sodium phosphate. I cannot compare moles of sodium with particles of sodium phosphate, for example. So I can only compare moles and particles if it's the same substance. If I have different substances, like here I have sodium versus sodium phosphate, I can compare different substances only if I'm comparing moles to moles or particles to particles. So let's just, for fun on this side, say I have one particle, one formula unit of Na3PO4. Well, that one particle has 3 atoms of sodium, 1 atom of phosphorus, and 4 atoms of oxygen, right? In one formula unit of Na3PO4. What if I had 1 mole of Na3PO4? Then I'd have 3 moles of sodium, 1 mole of phosphorus, and 4 moles of oxygen. Because a mole just means a number, like a dozen or something like that. So if I had 1 mole of Na3PO4, in 1 mole of Na3PO4, I'd have 3 moles of sodium. So to answer this, you would take 40.5 times 3 divided by 1 in your calculator. Go ahead and punch that in. 40.5 is 3 6 figs. And 3 is a counting number, like we actually count it. It's not a measurement, and so that has an unlimited number of 6 figs. So your answer should have 3 6 figs, just like the 40.5. Let's see, which one is that one? I got 122 moles of sodium as my answer. Because my moles of sodium phosphate canceled, and I end up with moles of sodium for my answer. Let's try number 12 together. How many atoms of oxygen are in 3.98 moles of MnO2? Ooh, that's a hard one. So let's start with what we have, 3.98 moles of MnO2. I'm going to start my conversion factor. On the bottom, I want moles of MnO2, so they cancel. On top, I would like to put atoms of oxygen. Don't write that yet. I'm going to go ahead and write it, but do not write it. Atoms of oxygen. What's wrong with this? Can I compare between moles and particles? Well, yeah, I can compare between moles and particles, right? We talked about this for a while now. 1 mole is that many particles, but only if it's the same substance. Are these the same thing? They're not. Oxygen is not the same thing as MnO2. So I can only use Avogadro's number to go from moles to particles or particles to moles if they are the same substance. Well, these are not the same substance, so I cannot do that, which means I need to do this in 2 steps. So I'm going to go ahead and erase that. And let's think about, what can I do? Well, we had just said that to compare between different substances, like when we talked about sodium and sodium phosphate, we can compare between particles, you can do that, or between moles. So there's 2 ways to do this. You can, since you need to go to a different substance, you can compare between the 2 substances using moles. So I can go from moles of MnO2 to moles of oxygen. And I know that if I have 1 mole of MnO2, I have 2 moles of oxygen. Now my moles of MnO2 cancel, and my units are now moles of oxygen. Then I do a second step, and now that my moles of oxygen are on top, I put moles of oxygen on the bottom so they cancel. And now I can also put atoms of oxygen here, because now I have the same substance, and I can go from moles to particles of the same substance using Avogadro's number. 1 mole is 6.022 times 10 to the 23rd particles. My moles of oxygen cancel, and I end up with atoms of oxygen. And for this one, I got 4.79 times 10 to the 24th atoms of oxygen. To get that, everything on top you multiply, anything on the bottom you divide. So 3.98 times 2 times 6.022 times 10 to the 23rd, and then divide by 1. Let me show you a different way to do this. So what I could do is I can start with the number I have as usual. And I start my conversion factor on the bottom. I want moles of MnO2. And then I say, well, I want atoms of oxygen, which are particles of a different substance. Well, I can only go from moles to particles if it's the same substance. So what I could do is I could go to particles of MnO2. Now, since MnO2 is ionic, the particles are called formula units of MnO2. And I can say, well, 1 mole of MnO2 is 6.022 times 10 to the 23rd formula units of MnO2. Like I said, these are the same substance, so I can go from moles to particles. Right now, my moles of MnO2 cancel, and I'm at formula units of MnO2. And then, now that this is on top, I want the same units on the bottom, so they cancel. So formula units of MnO2. And now I can go to atoms of oxygen because I can go from particles to particles of different substances. Again, if they're different, you can go between particles or you can compare between moles. So I can say, well, if I have 1 formula unit of MnO2, I'd have 2 atoms of oxygen. And this should give you the same exact answer. You're still taking the 3.98 times Avogadro's number and then times 2. So 2 different ways to do it. I'd like you to try number 13. So stop the video, try it for a second, or try it for a minute, I should say. It's going to take a minute. And then look at the answer at the end, and I'll show you the work. So pause your video and then come back to it. So welcome back. Hopefully you tried it. So this is my work. You could do the red or the blue. You don't need to do both of them. But what I did was I started out with what I'm given, so 20.3 moles of AlCl3. And I put moles of AlCl3 on the bottom. And I realized, oh, I need like total moles, total atoms. So I need atoms of aluminum and chlorine, right? So I can't go directly. I have to go through 2 steps. So what I did was I said, well, every mole of AlCl3 has 1 mole of aluminum and 3 moles of chlorine, and so that's a total of 4 moles. And then I said, for every 1 mole of aluminum or chlorine, I have 6.022 times 10 to the 23 atoms of aluminum or chlorine. Another way to do it is to start with the 20.3 moles of aluminum chloride, and I can't hide this. Sorry. I put moles of aluminum chloride here and formula units of aluminum chloride here, so they're the same substance, and I can go from moles to particles of the same substance. And then on the bottom here, I put each formula unit of aluminum chloride has 1 atom of aluminum and 3 atoms of chlorine for 4 total atoms. And so either way you do it, you do 20.3 times 4 times Avogadro's number, which gives you 4.89 times 10 to the 24 atoms total. All right, so the rest of the worksheet is your homework. The answers are at the bottom of the worksheet, so you can compare your answers to what you should actually get. Actually, I can't remember if they're at the bottom of the worksheet or if they're at the end of the worksheet, so check, but they are in the packet. So make sure that you do your work and then check the answer key and let me know if you have any questions. Hope you guys have a great day. Bye.